This is the 2019 FRQ for both Calculus AB and BC. This is question number 4. So there's a lot of information here, so I'm going to kind of annotate it. I highly recommend you do that. So the barrel has a ooh, you don't want that. We want this. The barrel has a diameter of 2 feet. So that's already given here. So we really don't need to do anything with that. The water drains out of the valve, not shown at the bottom of the barrel. So just for your own head, realize there's some kind of a spout out here. And what's happening? Water's draining out. So to give you there are the drops of water coming out. So what do we know here? So we're told the rate of change, that's a derivative of the height with respect to time. So I am going to write that down here. That's the change in height as time changes, the derivative. Oh, they give you that. This is redundant, but oops, daisies. I'll just do this. Now I'm going to change it to 1/2 power because we're probably going to have to take the derivative, and it's easier to work with that. H is measured in feet and T in seconds, so it's going to be feet per second. And the volume of the cylinder, they give us that formula. How nice of them. The volume is the area of the base, which is pi r squared, times the height. Now, part A is asking us to find the rate of change of the volume of water with respect to time. That's how fast volume is changing. So they're asking for dV dt, and that's a question mark, when the height is 4. So when h equals 4 at that particular time. And very important, they want units of measure. So we can't forget that. So with our equation on the right here, we have an equation. Again, there are key variables that we need, I'll point out. We need h and v. Those are the two things we need. There's v and there's h. Here's the problem. We have an extra variable r that we don't want. Because if we take the derivative of the formula as it is, we're going to get a third rate, dr dt. And since we know nothing about dr dt, that is going to be a problem. So we need an equation for r. We're going to have to rewrite that. But we don't, because r is a constant. Looky here. This right here, we have a diameter of 2. So if the diameter is 2 feet, clearly r is 1 foot. Lo and behold, it makes our life easier. So now our volume formula is this, pi times 1 squared times h. Now we take the derivative of each side with respect to time. So the important thing to understand that t is our variable. That is not t. That is not t. Those are actually functions. The volume changes as time changes, so that is a function of time, and h is a function of time. So when you take the derivative, you're taking the derivative of a function, not a variable. So the derivative of v would be dv dt, and the derivative of h would be dh dt. Now we're on the home stretch. So dv dt, we want to find that when h is 4, that will equal pi times dh dt when h equals 4. So some side work over here, dh dt when h is 4, I should have gave myself more room on this side. So sad. So I'm going to take this formula right there that I just circled. Let me grab my mouse, you mouseketeers. Hopefully it's charged and working. I see not my mouse. Okay, we'll do without on this problem because I don't want to waste more time. So I'm going to plug 4 in for h into that formula. You know, I'm going to give myself some room. So I'm going to do it a little higher here. dH dt when h is 4 is negative 1/10, 4 to the 1/2 power, and that is going to be negative 1/5. So it's going to equal pi times negative 1/5, and the unit of dH dt, that was feet per second. So this will be, okay, we need to talk here. This will be feet per second, but the units of this guy here, that was a radius. That's going to be square feet. So if we bring that down to the work we just did, we also have square feet. So we get negative pi over 5 cubic feet per second, and that should totally make sense because the volume is cubic feet. Therefore, that change of volume has to be in cubic feet, and the time units are seconds. So that is part A. Let's move on to part B. So part B is asking us when the height of the water is 3, is the rate of change of the height of the water with respect to time increasing or decreasing? You guys, do you see the key words there? I hope you do, because there is definitely a key word there. I will show you. Increasing or decreasing. And you should think immediately, oh, the derivative positive or negative. That tells you increasing, decreasing. Now you want to know what is increasing or decreasing. The rate of change of the height. So that's the derivative. That's dH dt. So it's asking, is dH dt increasing or decreasing? Well, to find that out, we need the derivative of dH dt. So that's going to be the second derivative of dH dt. Well, they already gave us dH dt. So we need to take the derivative of that. And this is where you have to be very careful again, because t is our variable. This h here matches that h. That is a function, not a variable. So this you have to treat as a function, not as your variable, and it'll change how your derivative comes out. So to take the derivative left side, you get the second derivative, but the right side, it's negative 1/10 box to the 1/2. You bring the 1/2 out front, and you decrease the power by 1/2, but then you multiply by the derivative of the box, so you get all of that. Let me do some simplifying. Well, you know what? I'm not going to because, well, I might need to. Hold on. So negative 1/20, that's pretty easy. The negative h to the 1/2, that moves it to the bottom. So we get that. dH dt, I'm going to copy everything that we already had for dH dt. Oh, that is so beautiful. Because do you see the radical h's cancel? Oh, so nice. Whoa, is that a constant? Negative and negative is a positive? 1 over 200? That seems pretty crazy to me, but that's it. So we're pretty much done. So we know that dH dt is decreasing. So we can say dH dt, which is the rate of change of the height, is decreasing. increasing. Because d2, so the second derivative is positive when h is 3. So that's it. That's my justification. So first I had to find the second derivative to tell me what the derivative was doing. So that would have been part of your points. Then finding the dt. Oh, the second, I'm sorry, my brain is tripping out. Finding the first derivative, given the first derivative, finding the derivative, that's a point. And then that gives you the second derivative. So that was, I'm just looking at scoring guidelines, how you got your points. My answer's right. I'm just not sure how they got the points. Maybe for the idea of taking the derivative of the derivative, and then 1 point for actually finding it, I'm thinking. But then the justification was 1 point. So let's move on to part C. Let me put a big box around this. Whoa, that's weird. So at time t equals 0 seconds, the height of the water is 5. Use separation of variables to find an expression for h in terms of t. So they're telling you specifically use separation of variables. Now they're being nice because if you don't use separation of variables, you will get 0 points, nothing, if you didn't recognize it. If it just said solve for h in terms of t, and that's all it said, and you didn't recognize it, you'd be in trouble. So I'm going to assume on this problem that they didn't ask specifically. So they're telling us that h of 0 is 5. So they're giving us that. And we have dh dt. So if you have a differential equation, put h to the 1/2, you are trying to find the antiderivative. And I've mentioned this a few times, and hopefully it's making sense. Your variable's t, and that's not a t. That's your function. When you have a function and you're trying to take the antiderivative, it just doesn't work. You need the variable there. Or unless you could do a u sub or something, but clearly that's not going to work here. So in this case, you have to have or use separation of variables. We're going to get the h's on the left side and the t's on the right. So divide both sides by h to the 1/2. On the right side, it'll disappear. I'm going to leave any constant on the right side. It just makes life easier. And at this point, let me rewrite the left side because I cannot take the integral of the left side unless I move the h to the 1/2 to the top. Now I integrate both sides. And the left side, I add 1 to the exponent and divide by that. On the right side, the antiderivative constant is just a constant times your variable, and we need a plus c. So we got 1 point for all of that. Now for solving for c, we're going to get another point. So side work, I'll do it over here. We know that h of 0 is 5. I'm going to plug that in. Oh, I forgot my mouse isn't working. I'm going to plug that into this equation here that we just found because we know that is an equation that always works. So we're plugging 5 for h. So 1/2 power is square root over 1/2 equals negative 1/10 times 0 plus c. So c comes out to be 2 radical 5. So you get a point for doing that. Your last point is solving for h. I'm going to pull that 1/2, make that 2, because you multiply by the reciprocal of 2. Oopsie. Plus 2 radical 5. I divide everything by 2. So this could be negative 1/20th t plus radical 5. Then I'm going to square both sides. And that is my final answer. I am finished, and that's it.